very strange one. Before we go to center of mass, it is what is called, it's a slightly complex chapter or complex section. It is what is called vertical circular motion. Vertical circular motion. Many questions are asked in this section. So essentially, my idea is this. My idea is combine work energy and to certain extent circular motion concepts. That is my idea. So this topic actually does that. It is combining work energy and circular motion. So let's see what is the main idea here. I have a ball of mass m which is connected to a string of length L, and it is fixed here. So this is the fixed point. Now I am giving some velocity to this ball. Let me call it u. And my idea is I should give such a velocity so that it goes in a circle like this and comes back, and we are assuming there is no air resistance, so it continues to go in circle forever actually. So my idea is I have to find u so that the ball goes in circle. Only the ball has mass m, string is massless. String is massless. If the string, or if you attach a rod sometimes, and if it has mass, either the string or the rod connected to the ball has mass, then it goes into a different chapter, rotational dynamics. We will see such questions later. But as of now, if you connect the ball with a string, the string is supposed to be massless, or even if you connect it with a rod, the rod should be massless. So with these ideas, now I have to find u so that it goes in a circle. So the question is, will, if I give any velocity, will it go in a circle? No, it may not go in a circle. Let us see what are the possibilities. So I have this thread and ball. Suppose if I give a very small velocity, it might actually go somewhere to this location, and it may stop and come back, and again go on this side again to certain height and come back. So it's not going in a circular path, it's oscillating. So if I give a very small velocity, it will go, stop, come back, go this side, stop. So it will be doing this oscillation. So not every velocity will make it go in a circle. So one possibility that we must be careful is we should give such a velocity so that it doesn't stop before completing the circle. So we should give such a velocity that it should not stop in the process of completing the circle. There is also another danger. See, suppose I gave it some velocity, it will go somewhere, the string becomes a slackened, and it then starts coming like this. It is not going in a circular path. Somewhere the tension in the string became zero, and after that the path of the ball is a projectile, because there is no tension, only gravity is there. It's going in a projectile. So if t equal to 0 during the process of completing circle, it won't go in circle. So there are these two dangers. One danger is it will stop before completing circle, Other danger is it will lose tension and not go in circular path and go in some other path. So we have to overcome these dangers. If you want to go in a circular path, you have to overcome these dangers. Now, what we will do, we will split this analysis into four quadrants. So the ball is given a velocity u. You could have even given a velocity this side. Okay, so it doesn't matter. I am giving it velocity to the right side. And this is the point of suspension. So I just divide this motion into four quadrants. I call this first quadrant, just the way we do it in mathematics. This is my second quadrant, this is my third quadrant, and this is my fourth quadrant. Now, string length, let me say it is L. Now, first I am doing some analysis related to fourth quadrant analysis. Fourth quadrant analysis. See, when you give a very small velocity to the ball may stop somewhere in fourth quadrant. If you give a small push, it might go till here, stop and come back. Or if slightly more push, it might go further distance. So there is every possibility for ball to stop in fourth quadrant. There is every possibility for ball to stop in fourth quadrant. So we should avoid this stopping because we want the ball to complete the circle. We should avoid this stopping. Otherwise, the ball will not go in a circular path if it stops. If it stops, then comes back and so on. Now, let me tell you some interesting things about fourth quadrant. So, ball can stop in fourth quadrant. However, tension can never become zero in fourth quadrant. You can try it practically also. You can feel it. There is no way that while the ball is going, the string slackens, string becomes loose, and ball suddenly goes like this. It doesn't happen in fourth quadrant. You try it. You take a small stone and tie it to a string, and then do this experiment. You try your best to make tension zero in fourth quadrant. Anywhere, it's not possible. We will even see this mathematically also. So what is the mathematics here? So this stone is going in a circular path. It can stop anywhere, but tension cannot be zero. So how do we check it? So what we will do? So in the fourth quadrant, somewhere when the ball is here and having a speed v, you actually gave a speed u. As the ball continues to go up, it is gaining potential energy because it's gaining height. So the speed will reduce. So by the time it comes here, the speed may be v. Okay, and it's obviously it went in a circular path here. So the tools that I have are, of course, Newton's laws. Newton's laws is one tool I have, and work energy is the other tool I have. So let me apply Newton's laws at this position when it is here. So let me draw the free body diagram. There is mg and there is this tension by the string. These are the only two forces that are there on the ball, no other force. We neglect air resistance everywhere. And let us say this angle is theta. So whenever any object goes in a circle, it is best to apply Newton's laws in the radial and tangential direction. Radial means towards center. Tangential means perpendicular to the radius. You can apply Newton's law in any direction. There is no restriction. But it is always convenient if a body is going in a circle. It is convenient to apply Newton's laws in the radial and tangential directions. These are very preferred. Why? Because when it is going in a circular path, I know the radial acceleration is v square by r. We have derived this in kinematics, v square by r. That is the radial acceleration. And tangential acceleration is rate of change of speed, not velocity, speed, dv by dt. So we know the acceleration is radial and tangential. So it is better to write Newton's laws in radial and tangential. Suppose instead of doing that, suppose if you are trying to write Newton's law in the vertical direction, you can write it, nothing wrong. But then the problem here is radial also has a component in vertical direction. Tangential also has a component in vertical. You must take both those components and write Newton's laws. For example, in our case, if I want to write Newton's law in the vertical direction, so I must have t cos theta minus mg is mv square by L cos theta minus m dv by dt sin theta. Something like this I have to write. Unnecessarily it will be very complex, Both the accelerations, the radial and tangential, are coming in this y direction. So it will unnecessarily become very complicated. So I am not writing that. So it's better to write Newton's laws in radial and tangential. So radial, there is already t in the radial direction towards center. Mg I'll split into mg cos theta, that's away from the radial, and mg sin theta, that's along the tangential. So we have t minus mg cos theta, net force in the radial, is mv square by r. This equation is of utmost importance for us right now. You can also write the tangential. Mg sin theta is minus m dv by dt. Minus because speed is reducing. So you can write mg sin theta is minus m dv by dt. This is the Newton's law in tangential direction. Okay, this tangential force is reducing the speed. That's how we interpret it. Okay, but let's focus on this Newton's law in radial direction. T minus mg cos theta is mv square by L. R is the radius, in which in our case L is the radius. It's going in a circle of radius L. So mv square by L. Where did we write this equation? We are writing this equation in the fourth quadrant, or if you give the velocity the other way, third quadrant, one of the two. We wrote this equation in third quadrant. So this equation is written in fourth quadrant. How same also holds for third. How you give velocity this way, it starts coming like this. Somewhere here you write. Okay, you get same equation. So this equation is valid in fourth and third quadrants, or third you can say. Now let us study this equation. Whenever you get a mathematical equation, it is better to give some values and understand it in more deeper way. So here you can see V0 is possible. Why? Because if V is 0, then you get T equal to mg cos theta. That's fine. You get some theta where there will be some tension and ball stop. However, if T is 0, this is impossible from the equation. Why? Let us see. If T is 0, you get minus mg cos theta is mv square by L. Here theta is a acute angle we have taken. So cos theta is positive. So this term is positive. Mg is positive, and you are getting v square as negative. That's an impossibility. So T0 gives v square negative. Impossible. Square cannot be negative. That means T cannot be 0 in this quadrant. That's what I was trying to tell previously also from feel, that in fourth quadrant T cannot be 0. Speed can be 0. Ball can stop. That's okay. However, T, tension cannot be 0, because there will always be, wherever the ball is, there will be some component of mg trying to pull the ball away, and that creates tension. So this is an important thing. So if you want it to, if you want the ball to go in a circle, if you want it to go in a circle, it should not stop in fourth quadrant. That is the first criteria. If it stops, our whole purpose is lost. It's not going in a circle. Suppose it came till here and stopped. Bad. It is not going in circle. Let us find the velocity required so that it stops at the boundary of first and fourth quadrant. This boundary. All these boundaries are very important. They are some critical cases. Let us find u so that it stops here, so that our velocity should be then more than that, right? I am trying to find the velocity required so that it stops at the boundary of first and fourth quadrant. Once I get that velocity, if you want to make it go in a circle, you should give a velocity more than that. So let's try to see this. So I have this ball. I gave you so that it exactly stops here. It exactly stops here. Okay. How do I get this u so that it stops there? I can use work energy. Why I can use work energy? Because you see, tension is a force which doesn't do work here, because it goes into our, if you go to our work energy chapter, it goes into special case 2. If force is perpendicular to ds at every moment, then f dot ds is 0. In this case, the tension wherever it is perpendicular to the ds at every moment. So work done by tension is 0. Then mg is a conservative force. So neither there are any non-conservative forces doing work, and we are taking whole universe as our system. So the remaining forces like mg are conservative. So mechanical energy is conserved. So I can equate potential plus kinetic at the bottom and at the top position. I'll take this as reference for calculating potential. If you take that as reference, at lowest point potential is 0, kinetic is half mu square. When it came to horizontal position, their kinetic is 0, it stopped. Potential is mgl because it went up by height l. So from here I get u as root 2 gl. So for u equal to root 2 gl, ball stops at boundary of first and fourth quadrant. Now it should be evident that for u less than root 2 gl, ball stops in fourth quadrant. You gave a lesser speed, it doesn't even go to the boundary. It stops before that only. It stops before that. Ball stops in fourth quadrant. So first thing is very clear to us. The speed which you should give to the ball so that it completes circle must first be more than root 2 gl. If you find anywhere the speed is less than root 2 gl, already circle is not complete. So that is the first thing. Now there is generally one question which you should ask in this chapter. Work energy methods are derived from Newton's laws only. It's an improvisation of Newton's laws. Work energy methods are modified form of Newton's laws only. Then, if that being the case, either you use Newton's law or you use work energy. No need to use both, right? But in this chapter, I will use both Newton's law and work energy. Why? This is a very perplexing question. Either Newton's law or work energy should suffice, because work energy methods have been derived from Newton's laws only. Then why in this chapter I am applying, at some places I am using Newton's law like this, and at other place I am using work energy? Why can't one thing suffice? So the answer is this. You see, you could have applied Newton's laws NLM in radial as well as tangential direction. That is one way. However, what we are doing is, in this chapter, we are applying Newton's law in tangential. We are applying Newton's law in radial. We are not applying in tangential. Corresponding to tangential, we are applying work energy. Now, the question comes, why can't you apply Newton's laws in tangential? You can apply, but it demands integration. That's one problem. Second, why can't you apply work energy in radial? Why work energy works only for tangential? The answer is, work energy, if you apply in radial, it gives a fantastic result, 0 equal to 0. It doesn't give you anything wrong, but it doesn't give you anything also. Okay, it's like, I did not teach any physics to you. Nothing wrong, but I suppose I did not teach. It's something like that. Work energy is not giving anything new or anything interesting in the radial direction. It says 0 equal to 0. Why like that? You see. See, suppose if this ball was there, if you look at the radial force, T, it doesn't do work because it is always perpendicular displacement. So work done by radial forces 0, and radial force will not even change the kinetic energy. So change in kinetic energy is also 0. Radial force will only change the direction of velocity. It won't change magnitude. For example, in uniform circular motion, we saw the force was only in the radial direction. Whatever it is, tension, gravity, it only changed the direction. It never changed the speed. So when the force is always perpendicular to velocity, it will only change the speed, not direction. And it will only change the direction, not speed. So when when force is perpendicular to velocity, it cannot change speed. This is a very important idea. So the radial forces are perpendicular to velocity, so they cannot change speed. If you remember, we drew some diagrams like this, I think so, where the force is perpendicular to velocity always, it won't change speed. The force makes some acute angle with velocity, it changes speed and also direction. The force makes obtuse angle with velocity, it reduces speed and changes direction. If force is along velocity, it changes speed but doesn't change direction. Same thing goes if force is opposite to velocity. These are all some vector diagrams which I remember as if drawing in work energy chapter. But anyway, so the case we are looking at is this: if force is perpendicular to velocity always, then it will only change direction, cannot change magnitude. So if that is the thing, and if you apply now the work energy in the radial direction, what do you get? Work done by radial force is 0, change in kinetic energy is 0. You get 0 equal to 0. Nothing wrong, but no use. So work energy in radial direction doesn't give me anything useful. So I have to apply Newton's laws in radial direction to get something meaningful. So I am applying Newton's law in radial direction, and work energy takes care of tangential direction. So I apply both ideas here in this chapter. So this is an interesting point. So I will use Newton's laws also, work energy also. If anybody challenges, why are you using both? You say, my Newton's laws is taking care of radial direction. I am applying Newton's laws in radial. And my work energy takes care of the tangential direction. So with that being the case, now let's go into the first quadrant analysis. So one thing is clear to me, that my speed should be more than root 2 GL. Otherwise, circle only will not be complete. It will stop in fourth quadrant. Now, let us do u greater than root 2 GL analysis. So basically here it enters into first quadrant. It enters into first quadrant. Why it entered into first quadrant? Because exactly root 2 GL, it stops at the boundary of first and fourth. Less than root 2 GL, if you give a speed, it will stop in fourth quadrant only. So you give something more than root 2 GL. So it crosses the boundary and enters into first quadrant. Now here there is another danger. The danger is this: in first quadrant, speed will never be 0. You try this experiment in the house, take a thread and stone, you give such a velocity to the stone that it will stop in first quadrant. It will stop and then fall vertically. That will never happen. The ball, once it enters first quadrant, it can never stop. What can happen? Tension can become 0. So it was going in nicely circle. Tension became 0 and it came like this. That is possible, but it never stopped. So the first, see, fourth quadrant, if you go back, in fourth quadrant, it could stop, but tension will never be 0 in fourth quadrant. In first, it is the reverse. It won't stop, but tension can be 0 here. So in first quadrant, V never zero, V not equal to 0. However, tension could be 0. However, T can become 0. So this is our danger. If T becomes 0, it won't go in circle, it will go in parabolic path. So our idea of taking the ball in a circular path is destroyed. So T should not become 0. Now let's look at the equations in this quadrant. See, let me, so I gave U here, and obviously U is more than root 2GL. So it crossed the fourth quadrant, entered the first. Somewhere here I am assuming the speed is V. Okay, this angle let us say is theta. There is tension. There is mg. So let's write Newton's law in radial direction, because work energy doesn't give anything meaningful in radial. It gives 0 equal to 0, which is not wrong, but work energy is useless in radial direction because radial forces don't do work. They don't change kinetic energy. So we have T plus mg sine theta, that is the net force in radial direction. How? T is already in radial direction. This angle is 90 minus theta. So component of mg in that direction is mg cos 90 minus theta or mg sine theta. So net force is mass into radial acceleration, m into v square by L. Now you see this equation, T0 is okay here. You will have some moment where T0, v square is positive. However, V0 is impossible. Why is it impossible? Let us see. If V equal to 0, then T is minus mg sine theta negative. T cannot be negative in a string. A string can only have a positive tension. It cannot, string can only pull an object. It cannot push an object. Suppose I connect a string to an object and ask you to push it. No, you can't. With a rod, you can push the object. So rod can take negative tension. Rods can withstand compressive force. Can withstand compressive force. That is T can be negative. That's okay. For rod. For string, T negative doesn't make sense. It will slacken. So if the ball is dropping in first quadrant, T is negative, but T cannot be negative. What would have happened? Even before T is negative, it would have been 0 at some point. Even before T is negative, it would have been 0 at some point. So before you reach this position where speed is 0 and tension is negative, before that point is reached, already somewhere else tension was 0 and it was going in parabolic path. So your equation for circular path is no more correct. So once again, let me reiterate this argument. If speed is 0, if the ball stops in this quadrant, at that point tension is negative. But hold on, before something can become negative, from positive something can become negative only through 0. Okay, so for example, I have money of 1 lakh, let's say, and suddenly tomorrow I went from 1 lakh to minus 1 lakh. How? Suppose I was investing in some gambling. 1 lakh became 90,000, 90,000 became 70, 70 became 50, 50 became 0. You have to pass through 0 at some point. No choice. And from there I go to minus 10,000, minus 20,000 and so on. So something, if it is negative, if it is taking negative from a positive value, in between there exists 0. So it has to pass through 0. So this tension, which was positive happily initially, now when the ball stops, you are saying it is negative. But before this stage is reached, before tension becomes negative, tension becomes 0. And when tension becomes 0, it is no more going in circular path. So you assumed that it continued in circle and you are writing some circular equation. That is bullshit. Already it lost a circular path previously only. So ball cannot stop in first quadrant. Tension can be 0. This is my idea. Now if tension is 0, my circle is not complete. So again I am in danger. So critical case, let us look at the critical case. The critical case is, I gave a velocity which is more than root 2GL. the ball entered first quadrant. If it loses tension somewhere 0 in first quadrant, it won't go in circle, it will go in parabola. So critical case is it should lose tension at the highest point here, because it almost completed one semicircle now. Now if it loses tension here, then as it crosses, again by symmetry tension will come in, because till here tension was there, it just became 0 here. By symmetry again it will become non-zero here and it will continue circle. So critical case is tension becomes 0 at highest point, T equal to 0 at highest point. Before that, if tension becomes 0, it won't go in circle. At highest point, if tension becomes 0, it has horizontal velocity, it tries to go horizontally, but the very instant it crosses that highest point, by symmetry, again string will have tension and it will bring it back in a circular path to lowest point, and the system will continue to go in circular path, assuming no air resistance. So if tension is 0 at highest point, suppose here the speed is v, then what is the three body diagram in the radial direction? Mg is there, tension just now became 0. T, I'll say it is 0. So mg plus T, which is 0 now, is mass into acceleration v square by L. This is one equation. So I applied Newton's law in radial direction. What about tangential? You can also apply Newton's law in tangential, but you have to integrate. Rather, I'll apply work energy. Work energy has nothing to do with radial. It will give 0 equal to 0. So at the lowest point, kinetic is half mu square. Potential is 0. At the highest, kinetic is half mv square. Potential is mg into 2L. So I used conservation of energy. So in one direction, I am using Newton's law. In another direction, I am using modified form of Newton's law, which is work energy. So I am doing good business here, nothing wrong. So from here, half mu square is half mv square. I'm going to substitute this from the upper equation, which is mgl plus 2mgl. So I get from here u is root 5gl after simplification. Okay, you take LCM, you get 5mgl by 2, and when you cancel, you get u is root 5gl. So this is the idea. So if you throw the ball with root 5gl, it completes circle, but still at the highest point tension is going to 0. So now my complete analysis is clear. So for safe circular motion, u should be more than root 5gl. Even equal to root 5gl, it is circle, but dangerous circle. Tension is 0 at highest point. So I will put an equality also, not an issue. So now my conditions are clear. If 0 less than u less than root 2gl, ball stops in fourth quadrant. U equal to root 2gl, ball stops at boundary of first and fourth quadrant. Ball stops at boundary of first and fourth quadrant, and root 2gl less than u less than or equal to root less than not equal to less than root 5gl, ball loses tension in first quadrant and starts going in parabolic path instead of circle. Starts going in parabola instead of circle. Why parabola? Because tension is disappeared. Now only gravity is there and velocity is at some angle. See, for example, suppose I gave root 7 by 2 gl, something like this. It went somewhere, tension became 0. From there onwards, the velocity is still there. Now it will go in a parabolic path like this, something like that. Okay, because once tension becomes 0, there is only gravity. It's like a projected ball now. Ball projected. So it goes in a parabolic path. That's the idea. Okay. Now, u greater than, sorry, U greater than or equal to root 5gl. Circle is complete. So this is very important. Same thing goes. So basically, if I take a stone with a string of length L, this velocity should be more than root 5gl to complete circle, or equal to also is fine. Critical case. This works even in our, there are some circus people going in a bike in a circular path. Suppose if I have a circular track like this and I have a block here, and the radius of this path is r, and I am asked what is the velocity you should give so that it completes circle. Now this case is very much similar to the string ball case. In the case of string ball, there was a tension pulling the ball. In our case, there is a normal by the surface pushing the ball. So either way, this force is towards center. So if u is less than root 2gr, the ball will stop, the block will stop somewhere in fourth quadrant and come back. If u equal to root 2gr, the block stops at boundary of first and fourth and comes back. If u greater than root 2gr but less than root 5gr, block goes, loses normal and comes in parabolic path, falls like this. If u is greater than or equal to root 5gr, circle is complete. Okay, so you see, if I want a block to go in a circular path on this track, of course this track has no friction, then u must be more than root 5gr. So if you are doing a circus bike, suppose if you came here with a force with a speed more than root 5gr, even if you don't accelerate the bike, you are safe. With bikes in circus, it's a different ball game, because friction is there, rolling is there, so many other complex concepts are coming there. We will see some of them in rotation. So that's not a very good example to take here, the circus bike. But still, suppose if it was a smooth surface where the bike wheel doesn't rotate, it's not a rotating bike where the wheel doesn't rotate. Suppose the bike is just sliding, it came with a speed more than root 5gr here, then it will successfully complete the circle. You need not do anything. If speed is lying between root 2gr and root 5gr, then there is a danger that it will lose contact. The rider may break his head if he is riding this motorcycle on a track where there is no friction. Okay, when there is no friction, it is as good as sliding. When there is no friction, uh, even your acceleration of bike will not have any effect. The wheel may rotate fast, but it slips on the floor. It doesn't increase the speed of the vehicle, right? If it is a frictionless surface, so the wheel is just slipping on the track, but bike's speed is not increasing if you accelerate it. So that case actually. So the string block case and the block with normal case, both are almost same. Now, what if I have a rod instead of a string? You see that? So let me try to draw a rod. So I have a rod and some ball is attached. The rod is massless, and let's say it's pivoted here. Now I give it some speed. What is the minimum speed so that it completes circle? With rod, there is no danger of, if tension becomes zero, it will go in parabolic path because rod cannot bend. See this rod case, even if it comes here, it can stop actually. The case where the rod is attached to the ball can stop here. There is no danger of, even if tension becomes zero, it cannot go in parabolic path because rod cannot bend. Rod can take even negative tension. In rod, tension can be negative. So there can be a compressive force in the rod. There can be elongative force in the rod, what we call as a tensile force or tension. It can even withstand a compressive force because it is a rigid body, unlike string. So in this case, what is the danger? It can stop anywhere, all the way from fourth quadrant to first quadrant. So the danger is it stops exactly at top point. Suppose if I gave it some velocity, it just came here and stopped. It completed half circle, unable to complete full circle. It stopped. So we can use conservation of energy and say half mu square is mg into 2l, or u will be root 4gl in that case. So any velocity less than or equal to root 4gl, circle won't be complete, because it can stop in fourth quadrant, it can stop in first quadrant. So u must be greater than root 4gl strictly. Even equal to will not work, it completes only half circle. So it should be greater than root 4gl. So you see, for a string ball system, it is root 5gl or 5gr. For a rod ball system, massless rod, it is slightly greater than root 4gl or root 4gr. So these differences are there. And sometimes they even do a trick. Suppose I have a track which looks like this. Okay, let me try to maybe arrange it a bit. Yeah, this looks good. Suppose this is a circular track. You can neglect this thickness. This is neglected. Very small difference, okay, between the inner and outer radii. And I have got a ball which almost exactly fits in between. So it's a pipe actually, in which I have a ball which almost exactly almost fits like that. And let's say this radius is r. My question is, what is the minimum speed so that it completes the circle? Think and tell me. Is it root 5gr? Is it root 4gr? Or is it something else here? No friction. Here it should be root 4gr. Na? Why? See, if it loses tension with the outer rim, there is the inner rim which will support it. It won't allow to go in a parabolic path, right? The inner rim, and it will take it in a circular path. So this system is similar to a rod only. Okay, if it loses normal force with this portion of the pipe, it will touch this portion. So somewhere here, it lost normal and wanted to go in parabolic path, but this section will support it and say, come on, forget your parabola, go in a circle. So it's like the rod case only. So here root 4gr is enough, or slightly more than root 4gr, for completing circle. The questions in this section are going to be sometimes extremely tough. Let me ask you first one question. Suppose I have got a ball, mass m, length l. Suppose I gave it a speed root gl. Find maximum height reached by ball. Just give a try. I'll just be back. Give a try. So I want you to find the maximum height reached by ball in this case. First, let us see where this velocity is lying between. We know that 0 less than u less than root 2 gl, it stops in fourth quadrant, right? And it's exactly that case. So it should stop somewhere here. Can I use work energy? Because the kinetic energy is gone and it became potential. So initially it had kinetic half m into v square. V square is gl. Now that became potential. So h will be L by 2. So it went to a height of, this is L by 2. You can even get this angle if you want. How to get that angle? This is again L by 2 because total is L, right? And I can use some cos theta, some trigonometry. Cos theta is 1 by 2. So theta is 60 degrees. So it swings by 60 degree before stopping. We can do that. However, the more challenging question is this. Suppose I gave a speed root 7 by 2 GL and I asked you maximum height. Students make the same mistake. They'll say initially it had kinetic half m into v square. Finally it becomes potential and they say h is 7 by 4L, which is a wrong answer. Why is it wrong? See, let's see what is the logic the student is using. Student says at the lowest point, if I take this as the reference, there is no potential energy, gravitational, only kinetic. Finally, he is assuming that at the highest point it stops. So kinetic is 0 and it has only potential. The problem is this concept. It stops at highest point. This is wrong. A ball need not stop at highest point. Best example is projectile. At the highest point, maximum height, is it stopping? No. It has horizontal velocity. So the criteria for maximum height, the concept for maximum height is not kinetic energy 0. Vertical velocity is 0. This is the concept. Okay. Of course, if it stops also vertical velocity is 0, but it need not stop. It could be moving horizontally. And that's the problem here. Now, why this doesn't work in this case? Because if you look at our initial velocity, root 7 by 2 GL, it lies between root 2 GL and root 5 GL. So it's our case where the ball goes into first quadrant, loses tension and starts going in a parabolic path. And once it is going in a parabolic path at highest point, it doesn't stop. So he got a wrong answer by applying work energy. So this problem cannot be solved with that. It's a tough question actually. So what you should do, let's do it. You gave a velocity root 7 by 2 GL, right? First is you should find where at what point does tension become 0 because it loses tension in this case. This root 7 by 2 GL is basically root 3.5 GL. Root 3.5 GL means it's more than root 2 GL. So it crosses fourth and enters first. But it's not root 5 GL. So it will lose tension somewhere. So let me find where it loses tension. If tension is 0 here somewhere, then mg sine theta is the only radial force. It should be mass into acceleration. So radial direction I have taken care, assuming the speed here is v. Radial direction I have taken care. What about tangential? I'll apply work energy. So at the lowest point, kinetic is half m into v square. Potential is 0. When it is losing tension, potential is mg L into 1 plus sine theta, right? Because this height is this height L plus this height L sine theta, where L is the length of the string. And kinetic is half mv square. At the point of losing tension, there is some speed. This is my second equation. So I have applied Newton's law in radial direction and work energy, which are our two core concepts in this chapter. From here, can I get theta and v? Yes, two equations, two unknowns. So let's solve it. 7 by 4 mgl is mgl into 1 plus sine theta plus half mv square. But mv square from first equation is mgl sine theta. So I get mgl can be cancelled. 7 by 4 is 1 plus sine theta by 2. So I get 3 by 4 is 3 by 2 sine theta. So I get sine theta equal to half, or theta is 30 degrees. So it entered into first quadrant, and 30 degrees after entering into first quadrant, it lost tension. Totally it moved 90 plus 30 or 120 degrees, you can say. What about V? If sine theta is half, okay, I can put that here and get V. V is root GL by 2. So V is root GL by 2. Now from here it goes in a parabolic path. So let's see that. Okay, this angle is theta. V is root GL by 2. This angle is also theta, which is 30. And it just lost tension. Still the velocity is perpendicular to radial because it just is about to end circular path. In circular path, velocity and radius make 90. So this angle will be 60. So it's like a projectile which is projected at 60 degree to horizontal, and you have to get maximum height here, this maximum height. So that maximum height is V square sine square theta by 2g. V square is GL by 2. Sine square theta dash, I'll say angle of projection. That is sine square 60. Angle of projection is 60. Sine 60 is root 3 by 2. So 3 by 4 by 2g. So that is 3gl by, sorry, g gets cancelled. 3l by 16. So this is 3l by 16. So what is the total maximum height reached by the ball? This L plus this L sine 30 plus this 3L by 16, right? So we have to add L plus L by 2 plus 3L by 16. 27L by 16. This is the maximum height from the lowest point reached by the ball. You see our previous answer? 7L by 4, wrong. The correct answer is 27L by 16. Had it gone in a circle, it would have gone to a maximum height 2L, which is, you can say, 32L by 16. This is if it goes in circle. It did not go in circle, so it went to a lesser height, 27L by 16. So this is the idea here. So the maximum height, you have to be very careful. You can't just calculate it, by using energy conservation. You can use energy conservation, but what is the misconception? At maximum height, speed is zero is wrong. At maximum height, vertical velocity is zero, horizontal could still be there. So you can't just speed is zero. Projectile also, you see, if I, this circular motion has a projectile in it, but even in projectile, at maximum height, there is horizontal velocity. So speed is not zero. So you can't use energy conservation in projectile with kinetic energy zero at highest point. No. You can use energy conservation with kinetic energy half mu cos theta whole square at highest point. Because at highest point, horizontal velocity is there, u cos theta. So that you can use. So these are the very important ideas. Now, what are the kind of tough questions which you can get in this chapter? They are very tough questions, at least at JE level. I want to do them because not because they come in neat. They may not. They may. I don't know. NEET has become tough nowadays. But it involves multiple concepts. So I have a ball. I don't know why it is not. Okay. So I have a ball. So one kind of question is this. I gave some velocity u, string length is L. I don't know what velocity I gave, but it went like this. Then somewhere it lost tension. So obviously I gave a velocity lying between root 2gl and root 5gl. Then it went in a parabolic path and it is exactly hitting here. This point of, suspension like this. So you see the ball was going in circular path in fourth quadrant. Then it entered first quadrant where it lost tension because you gave a velocity between root 2gl and root 5gl. And from there it went in parabolic path and ultimately it reached the point of suspension. You have to find u in terms of L and G, of course. L and G. Even in previous case, you see, I gave root 7 by 2 GL. The U I gave is root 7 by 2 GL. If I gave that U, it lost tension when theta is 30, and from there it went in parabolic path. Now I have to find this. This is one very complex question. Why it is complex? First I have to find where it loses tension, that angle. From there projectile, and that too it is exactly landing here. So I have to use all these ideas. So we will do it. This is one question. The other question is, okay, similar kind. I gave a velocity u which lies between root 2gl and root 5gl, goes, loses tension, from there comes in a projectile, but now it lands again at the point of projection. It is coming here, so I am unable to draw properly with free hand. Yeah, this is better. It is coming like this. So it lost tension, then from there it went in parabola and came to lowest point. Again I have to find u in terms of L and G. Find u. So these are the kind of questions, which will club multiple concepts. So there is circular motion here, there is work energy here, there is projectile here. So multi concept questions. So once we do them, we get a grip on all these chapters, whatever we have done. So let me first do this. This you can try as a homework. Let me do this question. Okay, it's a bit tough. Let's do it. So my string is of length L. I gave some velocity which I have to find. Okay, so that first it is losing tension somewhere here at an angle theta. From there it goes in a parabola and exactly comes here, right? Okay, suppose when it loses tension, speed is v. So I can write Newton's law in radial direction. There is mg, p became 0. So mg sine theta is mass into acceleration, which is v square by r in a circular path. It is just leaving circle there when tension becomes 0. That is one equation. Of course, I can conserve energy and relate u and v, but let me not bring u into picture right now. First, let me find v and theta. Okay, now how to find v and theta? I wrote Newton's law in radial direction. That is one equation. What is the other equation? The other equation is you have to use the information given. It's going in a projectile where this angle is 90 minus theta, and it's landing on the incline. It's landing here. It's like inclined projector, right? Like this, something like this. And you are throwing it perpendicular to incline. And what is the range here? The range is L. You see that? It's like an inclined projectile. So I have to use inclined projectile idea. Okay, and what is the uh, G? I can split G into G cos theta here and G sin theta here. So what is the time of light? In vertical displacement should be 0. So Sy is 0. Uy is V now. This is my vertical. This is my horizontal. I am taking inclined coordinate system. Acceleration in vertical is minus G cos theta. And I want time for this, for vertical displacement to be 0. Okay, so Sy is Uyt plus half Ayt square. So I got this time as 2V by G cos theta. In this time, it is traveling along x direction a distance L. Can you see this? Along the incline. So I'll apply x kinematics. Sx is uxt 0 because x direction velocity is 0 plus half gravity in x direction is g sine theta. Is it okay? My y-axis is this, my x-axis. Let me write in pink color only. My y-axis is this, my x-axis is this. So Sx is uxt. Ux is 0 because this velocity v was perpendicular in y direction. Plus half ax, which is g sine theta, t square. T I got 4v square by g square cos square theta. So from here, one g gets cancelled. So I have L equal to 2v square sine theta by cos square theta. This is my second equation. From 1 and 2, I can find v and theta. So let me find it. Here I can cancel m. So what is 1 saying? G sin theta is V square by L. And what is 2 saying? I forgot one G here. Okay. 2 is saying equation 2. L is 2V square sin theta by G cos square theta. L is 2V square sin theta by G cos square theta. Am I right? Just let me check it. Yeah. So from these two, I'll eliminate V square. So I have GL sin theta is GL cos square theta by 2 sin theta. So GL goes away. So I am getting theta now. So tan square theta is 1 by 2. So tan theta is 1 by root 2. I got. So from there, what will be V? Let me form a triangle. Tan theta is 1 by root 2. So what will be this hypotenuse? Root 3. So sin theta is 1 by root 3. I can plug it here. So V is root GL sin theta, which is 1 by root 3. That is V. If you know V, how to get U? You can use energy conservation now. At the lowest point, there is half mu square kinetic, no potential. When it loses tension, there is half mv square. We already found V. GL by root 3. V square is plus potential is mg L into 1 plus sine theta. What is sine theta? We just now got 1 by root 3. So from here, m can be cancelled. So if I simplify this, GL by 2 root 3 plus GL by root 3. So I can write it as GL plus 3GL by, I'm taking LCM. So I can say that is half U square. So U square is going to be 2GL plus root 3GL. So U is going to be root of 2 plus root 3GL. This is the speed with which if you project, the ball will directly hit the point of suspension. What did I do? Let's go back. Let's check a couple of these things. Okay. First is when it is losing tension, I wrote Newton's laws in radial direction. Then it is hitting the point of suspension, so I use some projectile idea. Okay. It's like inclined plane projectile. From there I get V and theta. Once you get V, you use energy conservation to get U. That's exactly what you have to do even in the previous question. This, whatever I gave homework. Only thing it is reaching here now. You cannot maybe do it like inclined projectile because it is losing tension here, and from there it's coming as projectile here. You can say, in this problem, my hint is this is a displacement in projectile. You can take it as, you can find this inclined project length. Can you find it? If you want, you can find it, or you can do vertical displacement, horizontal displacement. You apply kinematics like that, vertical and horizontal, and do it. Think about it. This is a good question, homework question. I am trying to give it to you. You do that and let me know what is the answer. You will be surprised with the answer. I am telling you, the answer will surprise you. So do it and let me know. So I'll end the class here. If you have any doubts, I'll take them up.